This is an elevator problem. So the first thing we want to think about is as we read the problem, there's a few things that we can put down. So as you're reading, it's not really an extra step, it's just as you're reading, you see that the mass of the person is 78.4 kilograms, so write that down. Stands on a scale inside an elevator, accelerates upward at 2 meters per second squared, so we know we have some upward acceleration, then a constant velocity, then slows to a stop, so that means velocity is 0 at the stop. We want to know the reading on the scale during each stage of motion. So the first thing we want to do is to draw a motion diagram that would represent accelerating up, then constant velocity. Constant velocity means nothing changes about the velocity, therefore the acceleration 0. And then slowing to a stop. So velocity and acceleration in the same direction for the speeding up, 0 acceleration for the constant velocity, acceleration and velocity and acceleration in opposite direction for the slowing down. We want to know the reading on the scale, so that is going to be a force. The scale exerts a normal force on the person. So our picture representation, because we don't have velocities and times and distances or positions, that means that really our best way of representing this is going to be 3 separate free body diagrams. So I'm just going to go ahead and put weight in for all of those, and I'm drawing them lined up with the motion diagram. So I've got 3 separate accelerations. That means I have to have 3 separate free body diagrams. If acceleration changes, then something changes in the free body diagram. So if I have acceleration up, that must mean that I have more up force than I do down force. The person is only in contact with the scale. So there has to be a normal force on the person by the scale. Weight vector is on the person by the earth. Normal is greater than weight, greater in magnitude, a bigger number of newtons. During the time when there's 0 acceleration, then normal and weight have to be equal length. And so we could say that during this time, normal would have to equal the weight so that I get balanced forces. Balanced forces means no acceleration. During the time that the acceleration is down, it's not because normal pushes down. The scale is definitely not going to pull the person down into it. The scale still pushes up on the person, but with less force. So therefore normal is less than weight because I need more down force. My picture doesn't reflect that incredibly well. Let me try that again. I need more down force than I have up force. So that acceleration is down because weight is a bigger vector than normal. So I'm trying to find that normal force, and so if a problem asks me about force, 100% of the time, if I need to know about a force, I'm going to write that. So that is Newton's second law. So if we are ever asked to apply Newton's second law, that's what we mean. That Newton's second law means sum of the forces equals ma, sometimes also called net force equals mass times acceleration, or the unbalanced force equals mass times acceleration. So the key step here is, in order to use this sum of the forces equals ma, I need to look at my free body diagram and put in the forces from my free body diagram. A helpful way to think about this is, first of all, this problem's all vertical. I'm not worrying anything about horizontal. There's nothing horizontal going on here. My sum of the forces is just going to be for vertical forces to tell me about vertical acceleration. I look at my free body diagram and I say, how many vertical forces am I working with? 2. That means there should be 2 terms on the left side of the equal sign for sum of the forces. Instead of writing sum of the forces, I'm going to have 2 terms, normal and weight, because there are 2 forces on my free body diagram. I subtract the normal and the weight because they are definitely not acting in the same direction. One's exerting force one way, the other's exerting force the opposite way. So I can't add them together because that would be implying that they're exerting forces in the same direction, that they're kind of working together, and they're not. The rule of thumb here is start with all of your positive forces, all of your forces that act in the positive direction. Subtract off all your forces that act in the negative direction. Subtracting weight really is just adding a negative because it acts in the negative direction. So that means I can solve for normal force if only I knew what the weight of the object is. So I have two options here. I'm just going to show you two ways to write it here. One is to substitute in, instead of writing W, I write mg because we know that W equals mg. The weight equals the mass in kilograms times the acceleration due to gravity equals ma. I can do this all in variables, nice and neat. And then I can now put in my number, 78.4 kilograms times positive 2. This is for the beginning of the motion. And then the g is 10 meters per second squared. Even though the problem doesn't really say that, sometimes it'll say, assume that g is 10 meters per second squared. But even if it doesn't, we're on Earth. If your problem takes place on Earth, then you're in pretty good shape there. To assume that g is 10. The more exact number is 9.8, but 10 works just fine. Then you can put this all in one line, actually, in your calculator. Your calculator is really good at order of operations. It will definitely multiply before it adds, and you get 940.8 newtons. You check, does that make sense? Well, I need an unbalanced force up. That means I need more up force than down force. So I would expect that my answer would be greater than the weight of the object, which is 784. Let's look at the other way of doing that. That would be where you actually go and calculate the weight of the object first. Perfectly fine, just show that equation so there's a reason for what you're doing. It doesn't just have a number come out of nowhere. So the weight of the object is in fact 784 newtons. So if I want to write it this other way, I would start with sum of the forces equals ma, and minus w equals ma, and minus, and then you just put in your number for the weight, and then you can put in your 78.4 times 2. Solve that, and sure enough, you're going to get the same. Writing W, you can substitute in mg, which is the mass times the acceleration due to gravity, or you can go calculate the weight and substitute that number in for capital W. The other two parts are required also, and I'll leave those for you to do. There's just checking in the n minus w equals ma will be exactly the same. The only difference is for the constant velocity portion, a is 0, so the whole right side becomes 0. For the downward acceleration, the acceleration is still a magnitude of 2, but this time it's negative 2. So you should get 3 different forces on the person for those examples. And you can experience that when you ride in an elevator. You feel heavier, you feel lighter, almost a moment of weightlessness. Okay, let's try this problem. We have a 600 Newton horizontal force. We have a 1,000 kilogram car. That one I'm actually going to label as an M. Maybe. Okay, so I can take the information from the problem. 600 newtons is some kind of a force. After pushing on the car on the pavement, its speed reaches 10 meters per second. Maybe it's easier to do over here. So what we can say is that we have some kind of force that's 600 newtons, just kind of assigning variables to things. We have a mass of a car is 1,000 kilograms. We know that the speed reaches 10 meters per second. I'm going to call that v because I know that that's some kind of a velocity just because of the unit. It then enters, there's something about 10 meters, and then we know the coefficient of kinetic friction is 0.7. Make sure you're good on that is a coefficient of kinetic friction, mu k. That is not script F. That is not a force, and we know it's not a force because it doesn't have a unit of newtons. we want to know whether the car will make it through the sand. So basically, we want to know whether the car is going to go 10 meters before it stops or not. Oh, I have to put that on there too. We actually have another velocity of stopped. That means that that's an initial velocity, and that one's a final velocity. So our motion diagram is the car is going to enter, and it's going to slow down to a stop. That means the acceleration has to be in the opposite direction of the acceleration. This problem does give me a whole bunch of velocities, right? So what I'm going to do is say that this is the positive x-axis. He's going to start at 0. And then I'm going to put it up here so I have a little more room. x0, t0, v0. I have an x1, maybe I have, we'll see. T1, v1. Everything's going to get filled in. And then I want to know what's going on with acceleration. Maybe I know a delta x, maybe I know a delta t. We'll figure out what I know. Okay, so the force of 600 newtons does not belong on a picture representation because the picture representation with all the positions and velocities doesn't have to do with forces. The mass doesn't belong there either. We define him as starting at 0 meters. The clock starts at 0. When he enters the sand, he is going 10 meters per second. We don't care anything about the previous history of the car. We actually don't know how far he goes, and we don't know the time. We're not given anything in units of seconds. You might think that the 10 meters is how far he goes, but the question is actually asking, will he go 10 meters or not? So what we want to know is how far he goes. The acceleration we don't know. We do know that he comes to a stop. Okay, one more thing that we need to put in here, of course, is a free body diagram because this problem has to do with forces. So we do a free body diagram. Normal and weight are equal to each other in this case because the ground is just going to hold him up. There's no other vertical forces. So we're pretty much done in a vertical direction. All we know is normal equals weight. Good to go. The guy is going to push with a force. I'm just going to call that the force on the car by the person. And then there's also friction. Now this one's a little interesting. We know there's friction because you're given a mu. Friction's going to oppose the motion. If the car is going to the right, friction will oppose that and will act to the left. We have to decide whether friction is the same length, longer or shorter than the guy's push. So let's take a look at our acceleration vector because that is the one and only way of answering that question. The acceleration vector points to the left. That means I need more left force than I do right force. That means I am in charge of drawing a friction force that is greater than the force that the guy is pushing with. That does not happen by chance. You have to decide that based on your analysis, generally from the motion diagram. Okay, so we want to know about a delta x. So as I look at finding delta x, that's screaming out to me motion equation. There's really no way of finding displacement other than using a motion equation. But if I try to find a motion equation, the only thing I know is VI and VF. And I want to know delta x, but I don't know A or T. So that's kind of a problem. I can't really do anything with a motion equation to figure out how far the car goes until I know either how much time or I know the acceleration. I have absolutely no way of finding the time, but I do have a way of finding the acceleration because acceleration is in motion equations, but it's also in the sum of the forces equals ma. So I'll just do what it says. My acceleration is in the horizontal direction, so therefore I'm going to sum the forces in the horizontal direction. And I look on my free body diagram and I have two horizontal forces, and I'm going to add up, start with all my forces in the positive direction, subtract off my forces in the negative direction, equals ma. This is going to let me find the acceleration. So let's see, I know that the push is 600, and so then I run into a problem. I need to know the force of friction. So I again have two options. I could just go over here and solve for the force of friction. Friction equals mu times the normal force. Mu is 0.7 because I've already identified that. I don't have to think too hard about that again. And then I need to know the normal force. I don't know the normal force, so here's my next problem that I have. I need to find normal force. Well, I look on my free body diagram and I see normal equals weight. And so I can go calculate the weight equals mg. And this car, I already wrote down, is 1,000 kilograms. That's what m stands for, is mass in kilograms, times the acceleration due to gravity, because I am on Earth, not because the car is actually in free fall. So the weight is 10,000 newtons. That means the normal force is 10,000 newtons, not because they're always equal, but because my free body diagram in my situation supported that. So normal force is 10,000 newtons. Multiply that, that would be 7,000 newtons. And you can plug that number in there for script F, friction. Another option is I could just write mu n instead of writing friction. Perfectly fine either way. And then I could write, now that that's 0.7, now I decide, okay, normal equals weight. Weight is mg, or I could just go put in my number. Any of those are fine. Equals, my mass is 1,000 kilograms. Make sure you keep your weight and your mass separate. Mass has units of kilogram. Weight has units of newtons. They are related numbers. They are not the same number. They are never the same number times A. So now I can solve this for A, because the whole left side is just putting numbers in the calculator. And then divide by 1,000 to get A by itself. So I get that the acceleration is 6.4 meters per second squared. Now that I know the acceleration, now I can go find, I'm going to do that over here, I can go find my delta x. So now I look on my motion equations, and I need a motion equation that has VF, VI, A, and delta x in it, and doesn't have t. The main requirement is that it doesn't have time in it, because I don't know time and I don't have any way of finding time. Don't lose the squared there. Now I put in my number. Oh, forgot to check whether my acceleration was reasonable or not. Mathematically, I got a negative number. I look on my motion diagram and I see that my acceleration vector points to the left. That means I better have gotten a negative number, or I would know that I did something wrong. Sometimes I see some algebra mistakes with this equation. The first thing you, well, okay, we get the 100 squared. We get to this, usually fairly easily. You cannot combine the 100 minus 12.8, because that would be like saying 3 minus 2x. You can't combine the 3 and the 2 if this was 3 minus 2x. If you're ever hesitating on how to solve something algebraically, a really good plan is to substitute in numbers that are just whole numbers, so it makes it look like it's an algebra problem, and sometimes it's easier to figure out what to do. Don't forget, you can always go back to the 7th grade version here of solve for it, put it back in the original. Does the left side equal the right side? If it doesn't, then you did something wrong. Make sure you've done enough problems that you've encountered those mistakes and solved them. Okay, so I get that delta x is a positive number. That makes sense because my motion diagram showed my object going to the right. And I get 7.8. So does he make it through the sand? No, because he comes to a stop after 7.8 meters, and the sand is 10 meters long. Hopefully that helped, and let me know if you need any further help.